Okay, this is Unit 9B, looking at linear modeling. When you see linear, hopefully embedded in there, you can see this word line. When we graph these kind of functions, they're going to look like straight lines. In the past, you may have heard slope-intercept form or a linear function. That's what we're talking about here. And we're going to go into a little bit more depth talking about the independent variable, the dependent variable, the rates of change, and some examples, and creating models for which a linear model will work well for us. So in Unit 9A, we were representing functions with tables and graphs. Now we're going to turn our full attention to a more common and versatile way of representing functions, and that is with equations. So although the equations are a lot more abstract than the pictures, they're a lot easier to manipulate mathematically, and they give us a lot of power when we're trying to create and analyze these mathematical models. Okay, so we're going to be able to understand the basic principles of mathematical modeling by focusing on the simplest models. That's these linear models, and these can go well beyond this: quadratic, cubic, and polynomial model. I mean, we can get all over the place in here, but these linear models are the most simple. They'll be represented by linear functions, and again, linear has that word line in it, so these will be straight line graphs. So as we look at linear functions, so let's imagine that we measure the depth of rain that's accumulating in a rain gauge as the steady rain falls. So we've got a nice steady flow of rain, in this case for 6 hours, and we want to describe how the rain depth varied with time during the storm. So in this situation, time would be the independent variable, and the rain depth is going to be the dependent variable, because at any given time, we could see how much rain is in there if we were to pick after an hour, after 4 hours, etc. And then, so suppose based on our measurements with the rain gauge, we find the rain depth function shown in this figure 9b. So we've got our lovely picture of the rain, and then here is what it looks like graphically. Okay, because the graph, when we took points of this measurement, the graph is a straight line, it is a linear function. And if we use this linear function as a model to predict rain depths at different times, then we are going to be using it as a linear model. So, if you look at this, if we follow our graph here in our straight line, this little idea here that you see, they're creating these little, so it's supposed to be triangles. I was trying to hook on to my point there. But those little triangles that are being created here, this is helping us determine how steep this is, or the rate of change. And so the rate of change is what we call the slope of the line. And notice that for every 1 hour I come across, I rise up 1 inch. So for every hour, I get another inch. Sorry, those aren't perfectly straight there, but we get this 1 inch over 1 hour, or 1 inch per hour, and that 1 inch per hour is what we call our rate of change. And the rate of change for a linear function is constant, meaning it's the same no matter whether you grab hour 1 or hour 4. For linear, it's a constant rate of change. Okay, so we just talked about this idea of a rate of change, and the linear function has a constant rate of change, and the graph is a straight line. So now we're going to look at 3 other steady rainstorms, but the constant rates of change are going to be different. For one rainstorm, it's 0.5 inches an hour, another it's 1.5, and for another it's 2 inches per hour. And you'll notice that the greater the rate of change, the steeper the graph becomes. And these little triangles that we're creating are going to help us represent the slope of each line, and the slope is going to be, and I'm really hopeful that you've heard this term more than once, but rise over run. It's our It's our dependent over our independent variable, or y over x when we're looking at it graphically. So you can see in each of these here, for every 1 hour we come across, we go up a ½ an inch in this one. This one, for every 1 hour across, we go up 1.5 inches. And then this one, for every hour we come across, we go up 2 inches. So again, rise over run, so you would need to take, in this case, 2 over 1, or 1.5 over 1, but it's always the dependent variable divided by the independent variable to get our rate of change. So that's just a look. Again, the greater the rate of change, the steeper the slope of our line. So let's look at some examples here. So we're going to consider the graph on number 13. In words, we're going to describe the function. We're going to find the slope of the line, express it as a rate of change. We're going to want to make sure we put our units in here. When we're talking about a model, we want units. We want more than just a number, but we want to identify what that number represents. And then we're going to briefly discuss the conditions under which a linear function is realistic model for the given situation. So we've got, in this model, it's kind of on its side, but we have distance from home and time in hours. So notice we start 500 miles away, and then 7 hours later that distance is 0. So if we were trying to describe this in English, you just something along the lines of you're 500 miles away from home and you travel at a constant rate of speed. So you'll want to include something like constant rate of speed towards your house for 7 hours, and then after 7 hours you arrive home. So that part A, just some kind of story along those lines. But again, the biggest idea is, since it's straight line, we have a constant rate of change, or constant rate of speed in this case. And because if we take our distance divided by time, that's going to be miles per hour. Okay, in part B, find the slope. So, and this is actually going to take a negative slope because this line from left to right is taking a downward trend. So it's going to be negative 500. That just means we're getting closer to our home. So negative 500 miles over 7 hours. And that's going to be our slope, negative 500 over 7. Or you can reduce that fraction down. Well, not reduce the fraction, but we can just get an approximation here, negative 71.4 miles per hour. All the negative means is that we're going towards our home. It helps us with our direction. And then part C, briefly describe the condition in which this linear function is realistic model. So, if you're going a constant rate of speed the whole way, then this is a good model. So this is good if your speed is constant. So this would be great for something like freeway travel, assuming you don't run into traffic jams or anything like that. This would be a terrible model if we're looking at stop and go traffic going through a city or something like that. But if we're looking at constant rates, and if we're in an airplane, this would be even better, because most of the time your airplane's going to get up to speed, and then you're going to fly at that speed for a significant amount of time with a little bit of variation possibly. But it's good, I should say, if the speed is constant. So that's a look at a model there. Just checking my time. Let's see. So next, so linear functions, again, in general, they have constant rate of change. They're straight lines, and the rate of change is equal to the slope. The greater the rate of change, the steeper the slope. And the way we can calculate the rate of change is by finding the slope between 2 points, and the slope is just the change in the dependent variable divided by the change in the independent variable. So that, again, that's our rise over run. So here's how much our dependent variable changed, here's how much our independent variable changed, and that's how we would find this rate of change. Okay, now we're going to look at something that can be helpful. It's called the rate of change rule, and this rule helps us calculate the change in the dependent variable from the change in the independent variable. So what we're doing is we're taking our rate of change. If you look, we had our rate of change was equal to the change in the dependent variable divided by the change in the independent variable. So I'm just going to abbreviate those. Notice if you multiply both sides by the change in independent variable, you'll get rate of change multiplied by change in the independent variable is equal to the change in the dependent variable. So you're just manipulating your rate of change formula in order to get this formula to see the change in the dependent variable. So it's not some magical formula we come up with. It's all based off of just manipulating this original formula right here. So we will begin a part 2 of this video by looking at a couple of questions in regards to the rate of change rule. Actually, I've got a little bit of time left. We're going to be tight on this one. So we're going to look at number 17 on this video. So we've got the water depth in the lake decreases at a rate of 2 inches per day. So when you see that per, that's usually getting towards your rate of change. So the rate of change here, and it's decreasing, so that's going to be negative 2 inches for every 1 day. And that's because of evaporation. So we want to know how much does the water depth change in 8 days, in 15 days. So when we look at this, we decrease 2 inches for every 1 day. So our independent variable here is going to be time. That's in the denominator there. Our dependent variable is going to be the depth, because that's in the numerator. And remember, time is always independent. So we've got our rate of change. So we're going to take our rate of change to find how much we decrease our water depth. So again, we're going to just take our rate of change and multiply by the change in the independent variable, which is in this case going to be 8 days and 15 days. So after 8 days, we would take, this is 2 inches for every 1 day, and this is a decrease of 2 inches for every 1 day. We're going to times it by change in time, which is 8 days. And notice that the days will cancel out in your units there. And this will be negative 16 inches. Or what you're going to put in your book or your answers, this is how the book does it. It says a 16-inch decrease is what it'll say for us here. So that's going to be how we would take on those problems. And then if we wanted to go after 15 days, again, you would just do 2 inches for every 1 day, times it by 15 days. And the days will cancel, and you'll get 30-inch, and this will be in decrease. So, again, that's how we would use this rate of change rule. We're just taking the rate of change, timesing it by our independent, or how much we're changing our independent variable, and then that will be how much the dependent variable changes over that time frame.